Okay, so in this module, we're going to talk about the early history of probability theory, how it developed, and its relationship to early, frankly, gambling games. And it's sort of a colorful history. So for this one, just kind of sit back, watch the video. You'll learn a little bit about history of probability theory, and this will all tie into how we interpret statistics today, even in some of the statistics we're running in SSD4R. So all of statistics rests on probability theory and the notion of randomness. And a random event is an event in the environment that we are unable to predict. So the outcomes are not predictable. Now that's a slightly different interpretation of pure randomness, in which the outcomes are truly unpredictable. In other words, we never will be able to predict the events. But for all intents and purposes, an outcome is functionally random if we are not able to predict events. And if we look at human history, we can go back to ancient dice and shaker games, where the dice were made of bone, and those could be animal bones or even human cadaver bones. But if you go back over time, people have been fascinated by the notion of randomness and gaming from very early on. In fact, there's a game called Knucklebone that we've seen in Greek statues. It's represented where you see figures who are kneeling or crouching, and it looks almost like kind of a backgammon game. We don't really know how it was played, but it's clear that there's a randomness element to the game. Now, there really wasn't a lot of sophisticated thinking about probability and the nature of chance until we get to Cardano in the early 1500s. And what's fascinating about Cardano is that he was a gambler. You know, he lost a lot of money gambling. He's noted that in his diaries. But as he was gambling, he really began to pay attention to the mathematical properties of gambling. So he's an Italian mathematician, very interested in gambling and dice games. And one of the first questions he asked was, what is the probability of rolling a 10 with 2 dice? Okay, what's the chance that it's going to come up? Because if you're a gambler, you really kind of want to know what the likelihood is. So the way that he sort of solved the problem, which makes a lot of sense to us today, seems very commonsensical, but at the time was not commonsensical at all, was to create a matrix. Okay, and across one axis he has the number of outcomes for the first die, and across the other axis the number of outcomes for the second die, and these outcomes constitute all of the possible outcomes. So if you have 6 outcomes on the first die and 6 outcomes on the second die, you just multiply the two together, 6 times 6, and there are 36 possible outcomes, meaning combinations of how the dice could fall. Now, then what he did is he just charted out which of these combinations would lead to the number 10 being the outcome. And he found out that there were three ways to roll a 10. Now there's 36 possible outcomes, 3 ways to roll a 10. That's 3 out of 36, or 1 in 12. So that's a very mathematical way to look at outcomes, and it gives information, especially to a gambler, about how the dice will fall. But even with this new sort of mathematical way of thinking about probability, it's tough to change the old ways of doing things, right? The old ways of thinking. So Cardano actually wrote, he says, "It is natural to wonder why those who throw the dice timidly are defeated. Does the mind itself have a presentiment of evil? But we must free men from error, for although this might be thought true, we have a more manifest reason. For when anyone begins to succumb to adverse fortune," notice right there the note on fortune as being the cause for events, "he is very often accustomed to throw the dice timidly. But if the adverse fortune persists, it will necessarily fall unfavorably." So what he's saying is, look, if bad fortune is out there, then you're going to throw the dice timidly, and then here comes the sort of secular feedback loop. Then since he threw it timidly, people think that it fell unfavorably for that very reason, but this is not so. It is because fortune is adverse that the die falls unfavorably, and because the die falls unfavorably, he loses, and because he loses, he throws the die timidly. Okay, so even though he's thinking more mathematically about outcomes, and he's thinking in terms of probability theory, these old habits die hard. We tend to think of this today in behavior analysis as superstitious learning, right? That events occur, and then we attribute the cause for those events to forces that are unseen. So now let's see how Cardano tried to solve a problem in probability theory. And what's interesting about this is he solved it incorrectly. But we'll see from the way he tried to solve it and the way it actually needs to be solved, sort of the emergence of the proper math for understanding probability theory. So Cardano concluded that if one throws a die, a single die, 3 times, the chance that a given number, for example a 6, will show up is 50%. And here's how he reasoned. He said if one chooses any 3 sides of the die, then one of those 3 sides are as likely to show as any of the other 3 sides. So he thought of this in terms of sets, like even numbers and odd numbers. I can easily throw a 1, a 3, or a 5, as well as a 2, a 4, or a 6. And so the odds of throwing odd or the odds of throwing even are equal. It's 50-50. Because I'm throwing the die 3 times, then the notion is that if there's a 50-50 chance that I will actually roll a 6. And at this point you might be going, I'm not sure about that last part. The first part kind of makes sense. The last part doesn't really make sense. But his conclusion was the odds are 50-50 that we will roll either a 1, a 3, or a 5 across 3 rolls. That means that the odds of rolling a 6 in one of the 3 rolls is 50-50. Now let's think about this, and let's do the math to actually show why this is an incorrect statement. Okay, here's how we'll think about it. What's the chance of rolling a 6? Well, if I blew up a single die and I looked at all the possible outcomes, I'd say, look, there's the 6. That's one outcome out of all the outcomes. So the chance of rolling a 6 is 1 in 6. What's the chance of not rolling a 6? Well, the chance of not rolling a 6 is 5 in 6. So if I add those probabilities together, they have to sum to 1.0, because 1.0 means we're accounting for all of the possible outcomes on the die roll. So to solve this problem correctly, we have to start by calculating the probability of not rolling a 6 on one of the 3 die rolls. Okay? So let's say we have the die, we roll it. What's the probability of not rolling a 6? Well, we already answered that, right? It's 5 in 6. So that's the probability of not rolling a 6 on roll 1. Well, what's the probability of not rolling a 6 on roll 2? Same probability, right? 5 and 6, and the same for roll 3. So if we multiply these all together, we get 5/6, right, to the third, because we're doing it 3 times. And that gives us a probability of 0.58. Now, what does that 0.58 represent? That 0.58 represents the probability of not rolling a 6 on any of the 3 rolls. Okay? So, if we were to ask ourselves, what's the probability of rolling a 6 on one of the 3 rolls, at least one of the 3 rolls, what we would do is we would subtract 0.58 from 1.0. Okay? So the 0.58 represents the probability of not rolling a 6 on one of the 3 die rolls. But that's not what we're asking. What we're asking is, what's the probability of rolling a 6? So all we do is we subtract that 0.58 from 1.0, we get 0.42. So what that means is there's a 42% chance of rolling a 6 on at least one of the 3 die rolls. Now the point of this is not for you to do the math and be able to figure this out. I'm not going to ask you that at any point in the class. The point of this is to show you that mathematically we can in fact predict the probabilities. It's important to note though that we're not predicting any single event. We're predicting probabilities of outcome over the long run. Okay, that takes us to Galileo, who kind of followed on Cardano's heels, and he wrote a paper called Thoughts on Dice Games. You know, it's probably one of the few times in scientific history that you're able to write a paper with a title like that and get published. But Galileo, he's not really well known for his probability theory, but his contribution was substantial. And so he asked a question, given 3 dice, why do the numbers 10 and 11 appear more frequently in throws than do the numbers 9 and 12? And he kind of did a similar thing. So what he did was he looked at the combination of all 3 dice. So if I were to roll these 3 dice over and over and over again, what are the combinations that could occur? And then what he found out is, look, if I had combinations that led to either a 9 or a 12, and I added up all those possible combinations, there are fewer of those than if I added up the number of combinations that would lead to a 10 or an 11. Because the 10 or 11 could appear more frequently in combinations, they had a higher probability of occurring. So, you know, this notion of the possible outcomes and the combinations of outcomes leading to a desired result, that's a very important part of probability theory. So then we take the next step And probability is a function of the total number of possible outcomes. How many possible outcomes are there when one rolls 3 die? Well, there's 6 possible outcomes on the first die, 6 possible outcomes on the second die, 6 possible outcomes on the third die. So we have 6 to the third. What that means is in his experiment here, there are 216 possible number sequences for all 3 die when rolled together. If we looked at the probability of rolling a 10 with all 3 of those dice, I should say dice rather than the die, that's 27 over 216, or 12.5%. Okay, so that's the higher probability. That's how we do the math for it. Okay, so let's go back to this notion of predicting specific events. It has become obvious to mathematicians that the probability to predict events in the long run could be solved with statistics, but not necessarily for predicting individual events that could occur at any one given time. So if I were to try to predict the roll of any individual die, all I know is that there's a 1 in 6 chance of rolling a 6, unless the die is not fair. If it's loaded in some way, then that would change. So what we're really going to need to do is to be able to understand distributions of possible die rolls over time. So can we gain greater accuracy in predicting distributions the more rolls that there are? So in other words, if given enough trials, is it the case that the actual empirical results that we had observed from all those die rolls would begin to equal those predicted by the mathematics of probabilities? Would the events we observe line up with our mathematical predictions? And that's coming next.